All right, guys. So I got a test tomorrow. We got to iron out any wrinkles we have. First thing Chris pointed out on my key on my little toolbox review. By the way, your answers will vary on some of this stuff and the way you write stuff out. The idea is to have the general idea, but I have too much on this. I fixed it, but I haven't had a chance to upload the new one. But it says if a function is continuous on the closed interval, and then I said and differentiable, it doesn't have to be differentiable. So it just has to be continuous on a closed. So that second part, you can ignore that part right there. But so as long as it's continuous on a closed, because like if it's continuous on a closed and it's got a cusp in it, there's still going to be a match, right? So as long as it's continuous is the point. You're going to have a max and a min if it's continuous on a closed. And also last year I saw a ton of people, for instance, I would give them a problem and I would tell them the interval was -1 to 3, okay? And they would say, and I would say, why do you know that the EVT works? And they would literally say the words, well, if the function is continuous on a closed interval. If you know the interval, say the function's continuous on, and put the bracket and the -3 in there. Does that make sense? Yeah. Or if you were to say, don't say differentiable on an open interval if you know the interval. Say differentiable on, and then put parentheses -1, 3 if it's open. Are you with me? So use the information if you have it. If you don't have it, like I don't in a general formula, then yeah, you could use the words of the A and B. But if you know the numbers, use them when you're dealing with that stuff. Hey, does anybody have a question at this point? If you don't, I'm just going to start going through some of the stuff that I had planned for today. But if you have a question for homework or anything like that, I do want to go back and do at least one of those where I give you all the information and you don't have to find it. So if you want to go back, I guess a couple pages, like look at this one. This is number 3. All right, so look at number 3 from yesterday. And let's just make sure that you're okay. And I'll show you the way I would do it. And I do this. When I do a number line, I'm not on your test. I'll probably ask you to do what it takes for a number line for like increasing and decreasing concavity. But when I'm using it, I want it to help me. So I'm not going to draw a bunch of number lines. I'm just going to put my information right here across the top. Okay. And you're going to see, because it's right there, I'm going to label what I know, like vertical asymptotes and x-intercepts and relative maxes and all inflection points. And then I'm going to look at this information across the top, and it's going to basically guide my pen. So I think that'll be the case for you too. But this is how I would do a problem like this if this was a test question and I had gathered this information. Okay, so I have this information. What is this top line telling me? The slopes are not. Be careful. There's a huge difference between increasing and positive, right? Positive means they look like this. Increase means they're getting bigger. Okay, big difference. This is saying slopes are positive. So all you know is what? The function is increasing, right? So the function's increasing, but not the slope's increasing. That's a difference, right? Are you with me? Do what? It would be a constant slope, perhaps. Yes. Now, not necessarily. All I know is that it's positive. It might be increasing. It might be decreasing along that situation. The slope might be. All I know is the function's positive. It has a positive slope. So what I'm going to do is I'm going to go, all right, -infinity to -8. I know that this has positive slopes. So I'm going to literally just put a little increasing there. Function's increasing. And then from -2 to -0.5, increasing. From 2 to 4, increasing. From 4 to infinity, increasing. I'm just going to put that in there, and it's going to be right there to help me when I start to graph this thing. All right? And then what do I know about the second line? Slopes are negative, which means the function is decreasing. So from -8 to -2, decreasing. and from -0.5 to 2, decreasing function. And most of the time, you're not going to have any place that's unmarked. Because I guess it's possible that a piecewise function would have a non-increasing, non-decreasing horizontal line, but polynomials don't behave that way. So it would have to be some weird piecewise function. All right, third line, what is that saying? Second derivative is positive, which means the function is concave up. And since I'm sketching the function, I'm putting this stuff here to help me with the sketch of the f. So this tells me function is concave up. Now, it also tells me that the slopes are increasing, but I don't care about that right now. I just want to know about the function. Function concave up from 0.5 to 4. So from +0.5, I'm going to use a different color here for fun. From +0.5 to 4, concave up. And from 7 to infinity, concave up. And then the fourth line, what does it tell me? Second derivative is negative, means the function is concave down. From -infinity to -2, concave down. From -2 to 1/2, concave down. From 4 to 7, concave down. And then they gave me a bunch of points that you happen to find. Evidently, they had some significance. Once I mark them, we'll go back and talk about the significance. So here are the points. I know there was a point at -8, -5. Does that happen to have any significance to you? Or was it just a point that they went and found because they figured they wanted to know something there? Yeah, look up at this right here and make sure you make these connections. What exists right there on the, oh, by the way, before I deal with these points, let's go ahead and mark the vertical asymptotes. All right. So there was a vertical asymptote at -2 because that's probably one of the first things you notice about a function, right? You look down at the bottom, you see it has a couple of factors down there. You can mark those VAs, and we've been doing VAs since pre-cal, maybe even some algebra 2, right? So I have those marked. So back to that, back to this -8, -5. Right here, what do you see since the slopes went from positive to negative? The first derivative test tells us what? There's a relative max. Now, the relative max was at -8. To find that -5, you would have had to plug -8 in the function, right? To get the -5. So the relative min is down there, but I'm going to want to mark that point. Okay? And that tells me there's a high spot right there. Maybe a cusp, maybe a corner. We'll figure that out in a second. All right, what about -0.5, 2? That's -0.5, 2 right there. What was significant about that? Look up. Yeah, look, another relative max, right? So there was another another relative max right there. So that's another high spot in the graph. Okay. What about 0.51? So +0.5 up 1. So +0.5 up 1 right there. That was a place where the inflection changed. Do you see that? I mean, yes.
Where are you getting the y values?
Evidently, see, I don't have the function here. This was so that I would have had to plug that value right there, that +0.5 or -0.5, back into the original function to get the y value. And since you don't know it, I had to give it to you. Oh, yeah. Yeah, why not? Because if I gave you the function and told you to find the information and you found it badly, like what if you made a mistake? Then what's going to happen to your graph? It's going to be a disaster, right? I mean, one small mistake. What if you accidentally graph x = 4 there, instead you put it over here? It's going to make everything so confusing. But I'm still going to want to see if you know what to do with information. So this is my way of breaking a problem up, right? I'm going to say, hey, what if I gave you the information? Now, if you still graph it wrong, I don't know how to help you. I mean, like, if you graph that over here, that's careless errors help. Hopefully, you'll put it in there and go, how on earth is this working here? This makes no sense. So hopefully, there'll be a red flag or two that will pop up. But anyway, so right there. And then what about the 0.20? What does it look like that was? Now, it could have been an x-intercept, and it is an x-intercept, but it actually did have some significance, right? You can see a relative min occurring right there. And then 5, 0. Now that's probably just an x-intercept. So that would have been someplace where you looked at the numerator and maybe the numerator was factored, right? And you went, oh yeah, look, there happens to be an x-intercept there. And then at 7, 2, look at that change in inflection from concave down to concave up. So I had change in inflection, change in inflection. Now, why wasn't there an inflection point here? Because there's a VA, right? You can't have a point where there's no points. And you can't have a max or min where there's none. Like some people right here would go, why isn't there a relative min right there? Well, there's a VA right there. That's why I always mark VAs on a graph, as well as the critical numbers, as well as the inflection points. I put them on there so I don't get confused and go, oh, there's a relative min there, or something like that. All right, so now here's what I'm going to do. I've got to navigate my way through all these points, okay? So if I've got all these points, let's see if we can make sense of it. And this is what I do right here. So I'm going to come in here, and I'm going to start sketching these patterns, and I'm only going to rethink a change in that thinking anytime I hit a critical number, a VA, critical number, inflection point, any of these places where you have either relative maxes and mins or inflection points or VAs. That's when I'm going to rethink what my graph looks like. And when I say, you'll see this in a second. All right, so here we go. All right, so right here, tell me what my graph is doing as I head towards this relative max. Increasing and what? Concave down. So heading towards this little relative max, I've got to be concave down, but rising. Are you seeing that? Well, I have no choice but to do something like this. You seeing that? I mean, how do I know if it's wider? I don't know. Is it steeper? I don't know. But that's something like, so yes, you could have drawn that. You could have drawn that. But you can't do this. Why? Because that would be concave down, but that would be increasing and decreasing. And this says only increasing. Are you with me? So pick something you feel good about. But remember, I can't go higher than that because that's a relative max. Are you seeing that? Now, notice I hit one of these important points. Now what happens? Decreasing, but still concave down, right? So at this point, now I can't go higher. If you do this, how could that happen? It said that's the relative max, right? So I've got to make sure I stay below this. Now, how do I go decreasing and concave down? I guess that, which kind of makes sense, doesn't it? Because there's a VA you're about to run into. So it looks like I'm just diving down there. Now, I'm very confident that the real graph looks better than this crap, right? So it's much more likely that this is nice and smooth through here. But again, I'm not looking for the most beautiful thing on the planet. So as long as the characteristics are there, you're okay. Now, I hit another important little break point, right? So what happens now between here and here? Increasing and concave down until you hit that relative max. Well, there's a VA, so what do you think it does? Increases and concave down, so it's diving down the asymptote, right? Now, I hit an important point. Now what is it doing? Decreasing, but still concave down. So now I'm decreasing, but concave down. But make sure that's your max, your relative max right there. All right, you hit another important point. Now what is it doing? Decreasing, but concave up. And that's a relative min, so don't go below it. And then what? Increasing, concave up, and there's a VA. So what do you think happens? Just follows that asymptote. On the other side of the asymptote, increasing and concave down all the way to there. So here it has to be, here it would have to be increasing and concave down. Whoa. Does that kind of meet those conditions? Increasing and concave down until you hit that high point. Actually, that's not a high point, but until you hit that inflection point, and then what happens? Still increasing, but now concave up. So now, if we already know, think about this. If we already know how to gather this information by taking a derivative and finding the critical numbers and checking to see if they change, or taking the second derivative and finding the inflection points and seeing if they change, and then put it all. And we already know how to find VAs. We already know how to tell if there's a relative max or min from here and define the Y value. We can put all this together. Literally, look what you just graphed. I mean, that's fairly impressive to think, man, I can graph really crazy looking polynomials by just pulling calculus together. Wow. So cool. But anyway, that's one of the things that I could potentially ask you on a test. And you only thought you could graph like basic stuff like parabolas.
On the test, or like supposed to determine like what the critical points that we have to like label them, or
I could ask you to label them. I might not. I don't think I said label these, did I?
I mean, you said determine.
Yeah. So yeah, I guess maybe if I said determine, I would be more clear. I think yes.
I'm looking at your key for number 5, and your critical numbers are 7 points. Is there any?
For critical numbers, I wrote points on this problem right here. Like this one?
No. Well, yes, that's the problem, but.
Okay, so on this one, do I have directions on these?
I think it's just a graph.
Yeah, so I probably was finding the points. If I had given you this and said list the critical numbers, you would have said -1 and 2 for your answer. I found those points so that I could plot them.
Okay.
But if I had said list critical numbers, -1, 2. Right here, if I say list possible inflection points, do not say 0 and 2. Take the 0, plug it in, and tell me 0, 0. Take the 2, plug it in, and whatever that gives me. Because points are points, and critical numbers are x values.
So it wouldn't be wrong if I just, like, you're not going to come up for the critical numbers when graphing this, like looking at.
Well, to graph them, you got to know where to put them, right? So, like, if I said, if you knew there was a critical number at -1, and it turned out that, like, where am I going to put it? You got to know where to mark it, right? So, if it's valuable, like if it ends up being a relative min, I want to know where to put it, so I'm going to need to plug it in there. But the answer to what are the critical numbers would be just the x values.
Okay.
Yeah, I didn't really say what to do on this, so I found them and used them. So that's probably why I have them listed. If I wrote on my key did I write on my key the critical numbers are and I had points?
Or it's a critical numbers and an arrow to the point.
Okay, good. Yeah, because what I did was I was probably pointing out, hey, these points came from you checking critical numbers and finding them. But the critical numbers themselves are just x values. Yes?
I know Claire asked this a few times last year, but like, what am I actually going to use this for? Like in the real
Mental
world?
weightlifting. And in this particular example,
Not like this particular example. I just like,
calculus in general shows up in all kinds of physics. I don't know what you're going to use it for, but in physics, it is all through position, velocity, acceleration. That's one example. In finance, when you're looking at growth rates of change of growth, when you're looking at how to maximize profits on a curve, there are lots of ways you can go in there and analyze a company's profits or costs and create a function that shows a pattern in its behavior and go, okay, we want to maximize profits. Do you see that you aren't producing at a place where you can maximize? You're down here. If you'd like to maximize profits, we need to increase production, maybe hire more people. And there are companies that will go in and analyze your company and say, hey, there's things that we can do. That's not cheap to get them to do that. But so I doubt that Sam's Sandwich Shop is having a guy come in and doing analytics and paying him hundreds of thousands of dollars. But somebody like Apple or Google or whatever would have people in there. Hey, we need to do things better. What can we do? So, but calculus shows up. And if you've seen the movie A Beautiful Mind, which is a really good movie, that guy, his theories that he came up were all calculus-based theories. He came up with when he was like 23 years old, won a Nobel Prize for it in his 50s or 60s. But calculus is so prevalent in economics and finance, and also just in physics applications, not to mention the math applications that you'll see. But yeah, there's a ton. You'll dabble in it a little bit. Heck, even a coroner to find out the time of death is going to use Newton's law of cooling. Now, granted, he probably has a table, I doubt he's like, give me a moment and does some calculus, but he's even using exponential growth and decay functions and might be integrating or doing a differential equation to figure out how long a corpse has been deceased based on its temperature. You know, at some point, it becomes so close to the room temperature, it's not useful, and they got to look at other things. But like if, for instance, if you walked into, found a crime scene, and I felt the temperature or measured the temperature of the victim, and his body temperature is normally running at 98.6, right? And all of a sudden it's 90 degrees, right? And you know room temperature is 72. There's a way to determine exactly how long he's been dead, or she, or whatever, just based on calculus. So there are a lot of applications out there, but yes, probably none in musical theater.
No, probably not. I was just wondering.
But definitely some out
Anybody
there.
else?
Right. Well, I what?
We do that problem number 5.
Check the key on something like this. I want to kind of get to more of what we're doing today. But look at the key on this. Guys, these are problems that are going to show up a ton. These literally all could be test questions. So when you're looking through these, be able to do all of these. Like right here, every continuous function on a closed interval is guaranteed to have a maximum in. What is that? The EVT. I'm not going to ask you what's the EVT and have you quote all these things, but I may give you a formula and say, what is it? You got to know it's EVT, not mean value theorem, not Rolle's theorem, not Fermat's theorem. The name for an x value, if either the derivative is 0 or the derivative does not exist, they will occur at relative maxes, mins, horizontal tangents, cusp corners, and vertical tangents. What are those? Critical numbers. All right. All of these, all right, this states that relative maxes and mins will only occur at critical numbers. So if you know the critical numbers, you will know the x values of any of your possible extremes. Fermat's theorem. Or Fermat, I don't know how to pronounce it. But these are things that you should know. They're all questions just jumping around. Number 4 looks pretty obvious. Continuous on that closed, differentiable on the open. When is the instant rate of change or the slope at a certain point going to be equal to the average rate of change? What theorem quotes that? MVT, right? Mean value theorem. You can use MVT, by the way, in calculus. What's this? Let F be continuous on a closed, differentiable on the open. If the y values at the endpoints are the same, then you're guaranteed at least one number where the slope is 0.
That's the Rolle's.
That's Rolle's, right? 6a. What does it mean if your derivative is greater than 0 on an interval? What do you know about f?
It has a positive slope.
Increasing. Now, yeah, you could say f has a positive slope, but that's not what they want because that's that, right? This is saying slopes are positive. So don't say if the slope is positive, then the slope is positive. That's a true statement, right? But it's not. They want to know, what do you know about f? F is increasing. Same thing about the next one, but it's decreasing. What if I say if f is increasing on an interval, then f is blank? I'm sorry. If f prime is increasing. Now be careful about that. These are the kinds of questions where I think it would be really wise for you to do what? Write that little table out, right? Write that table out where you go, you know what, I'm recording this. Write that table out where you go,
Oh, yeah.
okay, where you start out with, what do you know about f increasing? The derivative would be what? Greater than 0. We'll then take the derivative of both. That means that when the f prime is increasing, what? The second derivative is positive. I literally just took the derivative of both. And what do you know about the second derivative being positive? The first derivative is concave up. Write this down the second you get your test, or anytime you're dealing with relationships between f, f prime, f double prime. All right, what do you know about if the function's decreasing? The slopes are negative. Take the derivative of both. What do you know about if the slope is decreasing? The second derivative is negative. And if the second derivative is negative, what do you know about the function? Concave down. Have that burned in your brain so that when somebody now says, okay, now that I have that burned in my brain, these questions aren't tricky anymore. If f prime is increasing, What do I know about the function? If f prime is increasing, I know the function's concave up because I just look at my little table and go, oh, that was that line, right? F prime increasing, f double prime is positive, means the function's concave up. And you have that right there and you don't have to think anymore. You could also do this. Look, function, isn't the function getting bigger? Going from negative to 0 to positive? Functions, slopes, I'm sorry, aren't the slopes getting bigger? Slopes getting bigger, what does that form? Concave up, right? So the function is concave up. Pay really close attention to details like this and the fact that there's nothing there. Okay? So if the slopes are negative, well, we already did that. Anyway, move down. How about this? If C is a critical number that's differentiable everywhere and the slope changes from negative to positive, what do you know about the y value at that C? It's a relative min there, right? Slopes change from negative to positive. Then there's a relative min. So f of C is the y value there. So there's a relative min. Same thing on this one, but relative max. And what is this test called that I just did in 8A and 8B? The first derivative test. You're literally taking the first derivative, analyzing stuff, figure it out. What about this? If f prime is decreasing on an interval. So what is that? That doesn't say that the function's decreasing. It's saying that the what? The slopes are decreasing. Then what do you know about the second derivative? Negative. How do you know that? Oh my gosh. Well, how do you know that? You look at your little chart, right? You see f prime decreasing? I know when f prime decreases, the second derivative is negative, which means the function is concave down. Now, don't write the second derivative is concave down. The second derivative is not concave down. Second derivative is negative. It's the function that's concave down. Are y'all seeing that? Yeah.
Have you ever give us graphs that's like, this is the function graph? This is
Yes,
the prime,
absolutely.
but with the double prime or the function?
Sure. Why not? Anyway, anybody have a question on any of these they want to just jump to? All these are filled out on your on Schoology. Yes. 11A.
Yeah, I got it right.
The second derivative exists. If the second derivative is positive, then what do you know about the function? Function's concave up. But I could totally say, what do you know about the derivative of the function?
Well, it would be
It's increasing. So just pay really close attention. I literally will see people write that chart correctly on their paper and miss these questions. I don't know how. And on their test they look at it and they're like, ugh. Just be careful and notice whether it has a little, little apostrophe or quotations or whatever, the first derivative, second derivative, or nothing. All right?
Number 16.
16. C is a critical number. If the second derivative exists, hey guys, if the second derivative exists and the second derivative is 0, then the test is inconclusive. What test am I even talking about? The second derivative test. So it may be a relative max, maybe a relative min, or neither. And by the way, all 14 and 15. Go back to 14. If the second derivative exists, and when you plug a number into the second derivative, you get a positive number. What should that alone tell you? Positive second derivative should be concave up. Good? If C happens to be a critical number, though, in a concave up situation, what must exist there? A relative min. That's the second derivative test. The second derivative test is not a test for concavity. That's the test for concavity. Is the test for concavity, right? Yes, second derivatives being negative are concave down. Yes, second derivatives positive are concave up. But the second derivative test is in the family with the first derivative test. They are tests for relative maxes and mins. 15, the other one. If the second derivative exists, so you find the second derivative, you plug in a critical number and you find out that it's a negative value. What does that tell you? Well, negative tells you what? The function's concave down. Well, what if it's a critical number in that concave down? It must be a what there? Relative max there. Right? Which kind of goes against your when you see negative, you think, oh, relative min, and positive relative max. But no, negative means concave down, must have been a relative max. But again, it's got to be a critical number. If it's not a critical number, it could be this, right? There could be a big parentheses. If the critical numbers only are going to be here on those, you might have just checked that. Just because it's negative doesn't mean it's a relative max there. It would have to be at a C value right there. All right. And then when you go on to some of these other ones, like 17, find the critical numbers. What are you going to do? Take the derivative. Now, I see people all the time that will do this. All right, the derivative is low d high minus high times 1 d low over low squared. And they go and clean it up. 6x squared plus 6x minus 3x squared, ditto. And they end up with 3x squared plus 6x over x plus 1 squared. So here is their derivative. And then they go, okay, the derivative is 0 when the numerator is 0. And then they factor that. And they get 0 and negative 2. And then they say the derivative is dne when the denominator, x plus 1 squared, is 0. And then they solve that and they get x equals negative 1. And then they come in here and they tell me that these are the critical numbers. Where did I go wrong? Negative 1 is not in the domain. Now, it doesn't mean every time you do a DNE check that it's not in the domain, but clearly negative 1 is where the vertical asymptote is, right? So throw those out. AP doesn't really even require you to check those. So you don't even have to check them if you look up here and you notice right at the beginning, wait, x can't be negative 1. Well, I'm not even going to check that. And another thing you ought to check is if it gives you an interval like from negative 1 to 6, if I gave you an interval, is negative 2 even in your interval? Well, then I would throw that one out too then, if there was an interval. Now, there's not an interval, but if there was. Right? And we talked about Rolle's theorem, right? What are the 3 conditions? Continuous on. Don't tell me closed interval when you have an interval right there. It's continuous on bracketed 1 to 2. It's differentiable on parentheses 1 to 2. And what? So the f of 1, which you have to check it, right? Plug a 1 in there. 1, 10, 15, 9. And then you check the 2 in there. 16, 48, 36, 5. What's that? Negative 12, 4, up 9. So f of 1 is f of 2. Yeah, so that would be your third check, right? So you do all 3 checks and say, yes, roll sim applies. All right. And then that would be, what are the 3 conditions? So determine whether it can be applied. Yes, it can. And then if it says, if it doesn't apply, tell me why. And then it says, if it does, find C. So what do I do? How do I find where? F prime. So the derivative is 4x cubed minus 18x squared plus 18x, set it equal to 0, because that's the derivative has to be 0. So set it equal to 0 and solve. And I'm betting, well, factor out of 2x squared minus 9x plus 9. I'm betting you can get there if you just keep factoring. I know that I hate the 2 up front. I understand. But look, you can get there, right? So 0, 3 halves, and 3. And are those all in that interval? No, 0 is not in the interval. Neither is 3. So 1.5 is the only one in the interval. But we knew there was going to be one. Why? Because all 3 conditions were met. Now, if you found out that f of 1 was 9 and f of 2 was 10, the first thing I would do is go back and make sure you did the check correctly, right? Because there's a pretty good chance if I ask you about it, it will meet the conditions, but it might not. But I would definitely double check my math, right? Because sometimes the numbers get busy. But if the conditions are met, there has to be. Has to be. So maybe you factored wrong, or maybe something happened. Because that's a guaranteed theorem. You don't believe me? Go ask roll. And then number 19 is what we did yesterday, right? Yeah.
If that last one was, would you check, if it had a denominator, would you check the beginning?
Say it again.
Would you check the beginning? If it
For
has a
rolls?
denominator?
No, we're not finding critical numbers. We're just finding out where the derivative is 0. That's the rule, right? Yeah, and I could see how that could be confusing. Yeah, don't check where it doesn't exist. That's not the rule. The rule is saying basically if the slopes are 0 from beginning to end, which they are if the y values are the same, then the slope exists somewhere else. It's not suggesting that the slope is going to be DNE somewhere else. It's just saying the slope from beginning to end will match the slope somewhere in the middle, which is kind of a derivation of that mean value theorem. So I don't think something like this should be new, right? We know how to factor, hopefully. This one's been factored for you. So hopefully you're good on that. Critical numbers, points, right? Points are points. Critical numbers are x values. Increasing and decreasing are intervals. Relative mins and relative maxes are those points. What are they? Y values. I count off if you put points. Now, if you had to graph it, of course, find the point so you can mark it. But the max or min, and the reason why I do count off, you might be like, why? I'm just finding extra information. It's because AP will give you a test question, A, B, C, D, and one will be the x value, one will be the y value, one will be a point. I mean, they'll do that to you to see if you actually know what you're talking about. All right, so you have to be specific. And then concave up and concave down are intervals as well. No, you don't need to because it's assumed. Literally, relative min is a short name for the minimum y value in that related area. A max means the maximum y value. It's just an abbreviation for that. So it's understood. There's no need to put y equals, just put a value. And if it's killing you, you could always say, like to say more, you could always say something like, all right, the min is 7 at the x value of 1. If it's killing you to include it, you could say that, but at least you're specifying you know what the min is. But there's just no need. You don't need to do that. My key might do it to point out where they are, but there's no need for it. And that's not the answer. All right, here, mean value theorem problem. Still amazed every year. We've talked a lot more about it this year than some other years. But does this even hold? Are the conditions met? Is it continuous on the interval -2 to 2? Yes. Why? Polynomial. Is it differentiable on the interval from -2 to 2? With parentheses. Yes. Why? Polynomial. Polynomials don't have cusps and corners. They just don't have it. All right. So what is guaranteed since those two conditions were met? The derivative equals what? Slope from beginning to end. So how do I find slope from beginning to end? Find the point at the beginning and the point at the end and find slope. So what do I do with that? Once I have those points, I take the y value of that minus the y value of that and put it over the x value minus the x value. Now I got to go find that y value, right? Y minus, if you want to find them first, plug a -2 in, right? And I get 8 minus 6 is 2. So there's your first point. Plug in a +2, and I get 8 plus 6 is 14. So if you want to do that first, great. Here we go. Y minus y over x minus x. Set it equal to the slope. So I would do better than, like, it's never going to hurt you to go, the slope of x is f of 2 or f of -2 minus f, doesn't matter the order. It's never going to hurt you to actually quote the theorem. Because if you do the derivative wrong, they want to give you the point if you know what you're talking about. So it's never a bad idea to go, hey, I'm going to get 1 point for stating that. Find the derivative, you're probably going to get a point. Finding this simplified, which is what, -12 over -4, so 3. Is that right? 3. And then solving for x, in this case, it ends up being 0. So what value of c will make this true? 0. That's the x value on that interval. Sometimes they'll say, what's the slope? what is the slope of f of c? What would you answer there? Huh? What's the slope at that point? 3, right? There's literally saying the slope at that point is going to be the same as the slope from beginning to end. That's what this is saying. The instant slope matches the slope from beginning to end. So the slope is 3. Right? They've asked that question before. Right? But where does it occur? At 0. Right? Literally, this is what you just did. For those of you that are not catching this. At -2, I was here at 2. At +2, I was here at 14. There is a slope of 3 from beginning to end. Now, I don't know what this curve looks like. It's some parabola, right? So maybe it's doing this, right? But at 0, oh, that was actually pretty good. At 0, the slope there matches the slope there. But what was the slope at 0? 3, because it matched the slope from beginning to end. That's what it's saying. Find critical numbers. Use the second derivative test. Y'all know the second derivative test? What does it say?
It's finding relative max.
It's finding relative maxes and mins. It has nothing to do with, well, very little to do with concavity. Second derivative says if a critical number, which means I guess I got to find critical numbers first. So take the derivative, set it equal to 0, factor it. 0, -2/3, right? Critical numbers. Then plug those into the second derivative. Haven't done that yet, so 12x plus 4. So plug each of those into the second derivative, each critical number. When I plug a 0 into it, I get 4. When I plug a -2/3 into the second derivative, I get -4. I think. Yes. So what do I know? Second derivative test says what? When the second derivative of a critical number is positive, well, positive means that, right? But what does it mean if there's a critical number? Must be a relative min there. What does this mean? Second derivative, negative, tells you this. But what does it mean if that's a critical number? Relative max. Now, it doesn't mean that's the relative max. It means there's a relative max here. There's a relative min here, a relative max here. If I actually want the relative min and the max, what do? I have to go back and plug them back in the original. So the actual relative min is what? The relative min is -7. Because when I plug a 0 in, I get that. The relative max is some number. Yes, -130, -103. No, that's not right. Oh, what am I doing plugging a -4 in there? Sorry. Plug a -2/3 in there. If I got to plug a -2/3 in there, yeah, I try to be a little nicer probably on the real test. But I would have to figure that out. That would be the relative max, that big, ugly number.
Yeah, we're gonna get a problem like that.
I mean, I will, listen, that's not the end of the world, guys, right? It's -8 over 27 times 2, +4/9 times 2. I mean, it is, I hope you don't think that's the end of the world. Find a common denominator. I mean, I don't love finding common denominators of giant numbers like this, but I can do them, right? Just be patient and take your time and actually do them. But I try not to, if that's going to answer your question. But I'm not going to say that you're never going to see an ugly situation in APCalc.
I think I would rather eat a cactus than do a problem like that. I don't know.
Well, that may determine your
Future in the AP.
yes. Absolute extremes. People forget all about absolute extremes once they learn rules for finding relative extremes. How do you find an absolute extreme? Find critical numbers and take your endpoints and just do what? Plug them in. Do you have to check all the increasing and decreasing crap? No, that's for relative maxes and mins. Right? What if I didn't give you an interval?
Then just use the
Then
critical
you
number.
wouldn't, yeah.
Wait, then it's not.
What do you know about x to the fourth?
It's in.
If it's positive out front. Up to the left and up to the right. So what do you know?
There's not one.
There is not a max, but there might be a what?
Min.
A min. And the min would not be, there's no endpoints, right? So what would you check? You just check the critical numbers to see if there's a min, right? Plug them all in. You still have to use them. But most of the time when they're asking you about absolute, not most, some of the time when they ask you about absolute mins, if they give you an endpoint, check the endpoints, check the critical numbers. But I do know on this thing, if I didn't give you endpoints, then there's not going to be a max. But because I gave you endpoints, right? And you know it's continuous on a closed interval, what do you know by the EBT? There's going to be a max and a min. It just might occur at an endpoint.
I really wish.
What if I gave you this and said, hey, where are your critical numbers? Hey, what are critical numbers again? Places where the derivative is 0 D and E? Okay, where is it derivative or 0 in D and E? That looks like a 0 flattened out, right? This looks like a, maybe it went vertical right there. Look for those. That looks like it went 0. Now that didn't go vertical. That looks like a slope of 0. That's a slope of D and E, right? Cusp or corner. That's what? Now that's a hole. So even though the derivative didn't exist there, was there a point there? There's not a point there. So I can't call that a critical number if there's no point there. Can't do it. What about that? That's the slope of D and E. All of these x values, -9, -6, -5, -1, 1, not 3, 5, 6, 7, right? Not 9, even though it went horizontal, there's no point there. And not endpoints. This one didn't go anywhere. But all of those are critical numbers. Now, are they all relative maxes and mins? No. But if there are relative maxes and mins, they're going to occur there, right? At least that's what Fermat told us. Where are my points of inflection? Change in concavity, concave up, concave down. And this is what somebody said yesterday. How do you know exactly where, like right here, this switches from concave down to concave up? I don't know. Pick something. But just, it's going to be close. I try to make it occur at whole numbers. But if you look at that, you're like -6.1. Fine, right? Right? And then concave up switches to concave down somewhere in here, maybe. It's probably going to be at a whole number, but whatever. Concave down to there, and then concave up. Oh, that's an inflection point then. Concave up, concave up. Well, there's not even a point there. It doesn't exist. So even if it did switch, you couldn't say that. Concave up, concave down. There's an inflection point. Concave down, still concave down. Concave down, still concave down. Concave down, concave up. Is that an inflection point?
Nope.
Not if there's not a point. So now for points, don't write x values, right? Points, right? And then where's the graph decreasing? -infinity to -5. -1 to 1. Now remember, intervals don't say 1 to -3. It's decreasing. Increasing, decreasing, those are x values. Those are intervals along x. Parentheses, never brackets on that stuff, right? Decreasing, 3 to 5. Decreasing, 6 to 7. Y'all catching all this?
Mr. Wright, what is a second derivative? Like, what is it logically? I know we went over it last year. So like,
What is the second derivative? It's what I use to determine concavity.
yes, but
It's the rate of change of the slope.
okay.
Because if first derivative is the slope of f, and the second derivative is the slope of the slope, and slope rates change. So if you think about the second derivative, if it's positive, is telling you that your slopes are changing positively.
Oh, okay.
It's the slope of the slope.
Okay.
Yep. All right, guys. Cowboy up. that slope of this question. Like the slope is three. I didn't ask you that question here. I just said, what values of C will make this true? 0. But if my question was, what is the slope at that C value? Well, the slope, remember the whole mean value theorem says the slope at that C value is the same as the slope from beginning to end. So if the slope from beginning to end was 3, then the slope at 0 is 3.
Because I was looking here, I was like, ooh, the other side, like.
Yeah, you're using that to find where the slope matches. It matches when x is 0, right? So
I'm not gonna be here tomorrow.
that must be some good stuff going on tomorrow.
There's just not a game, so I think that's why a lot of people are going out of town. When can I make up my test?
Anytime on the makeup schedule. So just take a picture of that. There's 2 mornings, Monday and Friday,
Okay.
that are dark 30, like 6:50.
Ooh, okay.
And then there's 2 afternoons, Tuesdays and Thursdays,
Okay.
that are, I think, in the media center.
I have a dental appointment today, like right after school, but can I text you and see if you're still here after? Like, it's at 3:30, and they said it would take like 30 minutes.
Yeah, and I am way ahead right now, and it's so pretty out here.
You
I
might not be
don't
here.
know that I'm going to be here that day, but you are welcome to
I'll text
text
you.
to see. Yeah.
And no big deal if you're not. I can go this morning, but
Yeah, no worries.
I feel like after we did this today, I have a better